My name is Sebastian Seeds, and I'm a graduate student from the University of Connecticut. I'll give a brief summary of my poster, which outlines NTPE and answers some questions in the comments. This outline can be broken up into 4 broad sections: theory and impact, apparatus and kinematics, the hadron arm, and the electron arm. I'll finish up with a snapshot of the current analysis status. The neutron two-photon exchange experiment is a simultaneous measurement of the quasi-elastic neutron to proton cross-section. In order to discuss two-photon exchange, I must first say some words on the Rosenbluth slope and the Rosenbluth technique. Beginning at the top theory panel on the left, the nucleon cross-section can be parameterized into 2 terms, one that treats it like a point, the Mott term, and one that encodes the electric and magnetic form of the nucleon in the square brackets. Assuming a single virtual photon exchange dominates scattering interactions, one can plot the reduced cross-section against the virtual photon polarization epsilon, linear and epsilon. From 2 points, the Sachs form factors can be extracted. This is the Rosenbluth technique. The Rosenbluth slope, modulo tau, that depends only on the nucleonic q², is the form factor ratio. With 2 points, we expect to measure the Rosenbluth slope Sn. You can read about the experimental technique on the left. With a precision measurement of Sn, we will be able to distinguish between theoretical models that include 2 photon exchange corrections to Sn. Now a quick word on the form factor ratio puzzle. Fits to the world data for the Rosenbluth slope for the proton shows strong disagreement between measurements that employ the Rosenbluth technique and methods that use polarization transfer. While this discrepancy is well known for protons at q² up to 10 GeV², elastic EN scattering data are very sparse. NTPE will be the first such measurement in more than 50 years and the first to investigate TPE for the neutron ever. Now moving to the center top panel. The apparatus consists of the electron arm to detect scattered electrons and the hadron arm to detect scattered protons and neutrons. You can see a depiction of the full apparatus here. A breakdown of the expected error from the experiment can be found below, where we expect to be limited by systematics. Along with the 40-ton SBS dipole magnet, HCal is the hadron arm of the detector. I worked on both calorimeters, but along with Scott Barkas, I'm primarily responsible for the HCal. HCal is a segmented sampling calorimeter with 288 independent showering channels. Each module is read out by flash analog to digital converters, FADCs, and multi-hit time to digital converters, F1 TDCs. Together, they provide position, timing, and energy measurements for scattered hadrons in the experiment. In order for NTP to be successful, we need to clearly distinguish between protons and neutrons. This requires high position resolution and detection uniformity over the face of the detector. We're still in the preliminary stages of analysis, but so far the data are meeting our expectations from simulations. You can read more about it in this section. Onto the right panel, the electron arm is designed to provide precision timing, position, energy, and momentum reconstruction of scattered electrons. With this information, we can reconstruct electron tracks and select quasi-elastic scattering events. The big bite spectrometer is made up of several subsystems. The subsystems responsible for the trigger are the big bite pre-shower and shower calorimeters, or just BB-cal for short. Both are planes of lead glass blocks coupled to PMTs and read out by FADCs. This single-arm trigger registers an event with sufficient energy deposited in BB-cal over threshold. BB-cal can also be used as a pion veto via selection of low-energy events. We obtain precision timing of scattered electrons from the hodoscope. It consists of a plane of scintillating paddles read out by TDCs. Last but not least are the GEMs. Due to the high-rate environment, traditional wire chambers were replaced with gas electron multipliers to measure position information for scattered electrons. Combined with bend angle from the big bite magnet in front of big bite, momenta and tracks can be precisely reconstructed. Now for a brief synopsis on the analysis effort. Data has been collected and our statistics goals were met. Using the tools at our disposal, we were able to clear separation between protons and neutrons in HCal. All of the initial calibrations for the detectors have been finished, and we are currently waiting to reprocess 2 petabytes of data, more than Hall A has ever collected, through our first pass cooking. While we don't have any preliminary NTP results yet, we're on track to have our first figures by fall of this year. I'm happy to do my best to answer any questions below. Thanks for listening.